We'll do a little notes today, but without me here. We are going to take a look today at the law of cosines. I like to personally refer to the law of cosines as the Pythagorean theorem on steroids. And you'll see what I mean by that in just a little bit. So we've been dealing with the law of sines the last couple of days. So now today we want to look at the law of cosines. And so, right, the law of, just to scroll down, and we'll prove it here in a second, but right, the law of cosines is what we need to deal with these other two situations that we have not seen yet, right? So the law of cosines is going to allow us to deal with the SSS and the SAS, or the sassy situation, as I like to call it, right? So law of cosines is going to let us deal with those two, all right? But to do that, let's figure out what the heck the law of cosines is. So this proof is kind of, it's not something you have to know how to do, but at the same time, I think it's kind of cool just to see where it comes from. So if we have a good old triangle here and we cut it up, and so a couple things though we can do is what we're going to do, little sneaky thing here, is we're actually going to call this little section right here X. And then if we do that, right, then if A was the entire side, then that would mean that this little part here, right, is A minus X, right? So if this whole side is A, then we can call X that little bit, and then A minus X would be that other little bit. So we basically got two lovely little right triangles then, right? So we've got this right triangle here, right? And then we've got another right triangle over here, right? So we've got two right triangles. And so we're going to actually use the Pythagorean theorem. So we know that looking at the green triangle here, right, that x squared plus h squared equals b squared, right? Just good old Pythagorean theorem. And then if I look at that pink triangle, then I know that h squared plus a minus x squared equals c squared. Okay, so I can just write two different Pythagorean theorems there. And you'll notice that h is in common in both of them, right? So both of those equations have h squared in them. So if I solve these, right, then that means h squared equals b squared minus x squared. And then I also know that h squared equals c squared minus a minus x squared. So if that's true, right, if both of those are in terms of h, then I can set those equal to each other. So I know that b squared minus x squared must equal c squared minus a minus x squared. So there's kind of a big old messy looking equation that I know is true, right? And so then now it's all just algebra. So that means that b squared minus x squared would equal c squared minus, so if I multiply this out, right, a minus x times a minus x, I'd have a times a, so that's a squared. And then I'd have a negative ax and another negative ax, so minus 2ax's, right? And then I'd have plus x squared. And so then doing some more algebra, I can distribute that negative, so I get minus a squared plus 2ax minus x squared, right? And so you'll notice that we have an x squared on both sides. So if I add x squared to both sides, whoop, that's going to be gone. And so I'm going to just be left with b squared equals c squared minus a squared plus 2ax. So things have simplified quite a bit, but if you notice, right, if I go back to my original triangle, right, I know that I want to try to come up with a formula here that doesn't have x in it, because I don't typically know what x is, right? I normally am going to know the sides of the triangle, which would be a, b, and c. So one last thing to do is figure out how can I get rid of x right there. And so if this is called the law of cosines, I bet somehow I need to use a cosine, right? So if I come back here to my lovely little green triangle, I know that the cosine of angle C, right? So if I'm looking at angle C here, then its cosine would be the adjacent x over the hypotenuse b. So I know then that x over b. So then multiplying the b over, I know that x equals b cosine c. And so then I'm going to just substitute that in. So I know then that c squared minus a squared, and then I've got 2a, and then where x is going to be b cosine of c. So that is the law of cosines. Now, the only thing is we tend to do a little bit of manipulating on that, okay? And so the one thing that we tend to like to do is and so this technically is the law of cosines, but the way you're going to see it written is when you have angle C right here, what we actually want to do is get the c squared and the c on opposite sides. So the way we end up writing it typically is that if we add the a squared and subtract the other stuff to the other side, then we end up with c squared equals a squared plus b squared minus 2ab cosine of c. And that's usually how you're going to see it written. And so that is our law of cosines. And so this is why I call it the Pythagorean theorem on steroids, because if you look, c squared, right, equals a squared plus b squared. That is the Pythagorean theorem, right? And then it's just got this little bit of extra juice right here that allows me to deal with what if it's not a right triangle. So as a matter of fact, notice what happens if C was a right angle, right? What if angle C is 90 degrees, then the cosine of 90, right, would be up here. So the cosine of 90 is 0. And so notice then that this whole mess right here would just be 0, and I would be left with the Pythagorean theorem, c squared equals a squared plus b squared. Now, that is how we write it. We can move the letters around. Like, so for example, we could say a squared equals, and so then we could say that would be c squared plus b squared minus 2cb cosine of a. That'd be another way to write it. The main thing is that notice that whatever angle I choose here is the side over here. Okay, so across from each other in the equation, so if I use angle A, then side A is what goes over here. So again, I'm going to give you one version of it, and then you just kind of have to know what goes where. So really and truly, rather than trying to memorize a whole bunch of different versions of it, just pay attention to where things are, right? So if angle C is on one end of the equation, then that means side C is on the other side, okay? So let's just see it in use, and I think it'll make good sense for you, okay? All right, so we've got a triangle, and so let's draw a picture. So as always, you need to get a good picture of it, and we'll label it. So let's see what all we know here. So if I draw a triangle, I don't know why that didn't straighten out, but whatever. Okay, that one did. Okay, so let's say maybe this is angle Z down here, right? So then this would be 72 degrees. And so that would put side Z across from it, right? And I can pick whichever other two I want here. So maybe this is 12, but that would make this angle X. And then if this is what I'm going to call side Y, so then that's going to be 20, so that would make this angle Y. Okay, so notice that here's a case where I cannot use the law of sines, right? So in order to use the law of sines, I have to have a side across from an angle. And so when I look here, right, the only angle I have, I don't know the side across from it. And the sides that I have, I don't know the angles across from them. So that is what forces me, right? This is side, angle, side. So that forces me into, I've got to use the law of cosines. So as much as I'd like to avoid law of cosines, perhaps, I don't have any option here, okay? All right, so the way this works is, notice that the only angle I have is 72. So I know for my equation then, the only place that there's an angle in this equation is at the very end, right? The cosine of the angle. Everything else is a side length. So I know that that means that the only option is to put the 72 all the way down here at the end as the cosine of 72. If that is the case, now I just have to fill everything in. So wherever the angle is, 72, across from it is side Z. So across from it in the equation is side Z. So it's going to go over there. That means the other two sides would be 12 squared and 20 squared minus 2. That's part of the formula. And then it's those same two sides, 12 and 20. Right? So I literally just plug all that mess in. So again, if this is the only angle I know, right, then it goes across from in the equation the side that it's across from in the picture. And then I just fill in those other sides, okay? And then I just get out Desmos, right? So as soon as I just get out Desmos and I start punching stuff in, I think I actually already had it in there, but I'll go ahead and re-punch it in here. So again, make sure you're in degree mode. So I've got 12 squared plus 20 squared minus 2 times 12 times 20 times the cosine of 72. And so I get 395.67. So I know that z squared equals 395.67. And so the last thing to do then, don't leave it as that, and that you should realize, wait, a side length can't be 395.67 if the other sides are 12 and 20. So now I've got to take the square root of 395.67, and I get about 19.9. So z is about 19.9 centimeters. Right? I think it was in centimeters. Yes, 19.9 centimeters. Okay, now here's the thing. Once I have that, right, I can actually just use the law of sines to get the other angles, right? So once I have that, 19.9, now I'm just back to law of sines. So once I have one of the missing pieces, I can use the law of sines. So now it's just right back to, oh, well, the sine of 72 divided by 19.9 would equal the sine of x divided by 12, right? And so then if I just multiply that 12 over, so I'm going to have 12 sine of 72 over 19.9 equals the sine of x. So I'll just come over here to Desmos. So I've got 12 function sine of 72. And I'm going to divide that by 19.9. So I get 0.574 equals the sine of x. So last step, take the inverse sine, right, to figure out what the angle is. So the inverse sine of 0.574 is going to be about 35 degrees. 35 degrees is angle x. So I've got that. And then no reason to work hard now that I've got that, right? The last piece would just be, well, 180 minus the 72 degrees minus the 35 degrees is 73 degrees, and there's my last piece. Right? And then as far as the area goes, I can go back to my good old formula from this week. So I can just do 1/2. I've got my two flippers, right? So this one's set up perfect. I've got my flippers 12 and 20, and then I want to use the sine of the angle between my flippers, which would be the sine of 72. So then 0.5 times 12 times 20 times the sine of 72 is 114.1, 114.13 centimeters squared, 114.13 centimeters squared. Bam, done. Okay, so that's the SAS situation. All right, and then the next situation we want to look at, this is the last type, good old side, side, side. So what if I just had three sides? All right, so what if I just have three sides of a triangle? What do I do? All right, so let's say I'll just label these kind of, so this looks like the longest one, so I'll say that's 20, which is Q. So that makes this capital Q. And then that one looks a little shorter, so I'll call that P. So that makes this angle P, and then this one we'll say is 15. So that's R, so this makes that angle R, okay? So side, side, side. Notice we do not have an angle. right? So there's no angle at all. So the fact that I have no angle at all means I can't set up a proportion, so I'm stuck with the law of cosines, okay? Now, one thing that's very, very, very important to do when you have side, 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 always find the biggest angle first using the law of cosines. It's so important that you find the biggest angle first. And that is because once you have it, then when you go to use the law of sines to find the other parts, you won't run into the old SSA/ASS situation. So if you find the biggest angle first, you're going to be safe, okay? So when I look at this picture, I know the biggest angle is across from the biggest side, so that would be angle Q. That's what I'm going to use the law of cosines to find, okay? So I set it up. Now again, remember, there's only one place in the law of cosines where I can put an angle. So that's all the way down here at the end, the cosine of Q, right? So as soon as I put Q there, then that means on the other side of the equation, whoop, is where I put side Q. So they're across from each other in the picture, they're across from each other in the equation. And then I fill in the other parts. So now I know then that the other sides that I'm dealing with would be 10 squared and 15 squared minus 2 times 10 times 15. And that 2 is part of the formula, right? And the 10 and the 15, this 10 and 15 are going to be the same 2 that you got right there. So this one's just a little bit harder because now I have to actually solve for Q. Right, so when I go ahead and square this out, I'd have 400 equals 100 plus 225 minus 2 times 10 times 15 would be 300 cosine of Q. And so the biggest mistake I see here is then people will say, well, that's 325 minus 300 cosine Q. Now be careful. You cannot put these two things together. The 325 minus 300 are not going to combine because that 300 is attached to the cosine of Q, okay? So I cannot, right, this is all one term. So I cannot put the 325 and the 300 together. What I can do is subtract the 325 to the other side. So I have 75 equals negative 300 cosine of Q. I can divide by negative 300, so I have 75 over negative 300 equals the cosine of Q. And so then to solve for Q, I can take the inverse cosine of 75 over negative 300. And that's going to give me Q. So I get out good old Desmos, right? And I punch that mess into my calculator, and it turns out that the inverse cosine of 75 over negative 300 is 104.5 degrees. Now I have angle Q. So angle Q is 104.5 degrees. Again, as long as I found the biggest angle first, I'm safe now to use the law of sines, even though technically I'm now dealing with an SSA situation. But if I found the biggest angle first, I'm going to be safe. Okay, that ambiguity that we talked about is going to be okay. So now I can just set up my law of sines. So I have the sine of 104.5 degrees divided by 20 equals the sine of, so I can just pick one. I'll do P, sine of P over 10. So I multiply the 10 over. So I got 10 sine of 104.5 over 20 equals the sine of P. If I take the inverse sine, I find out that P is about 29 degrees, okay? So now I can put that up here, so 29 degrees, and then that last one, right? Super easy to get the last one because I can just subtract from 180, right? So 180 minus my 29 minus my 104.5 is going to give me 46.5 degrees as my last angle. And then my area, again, I can just pick which flippers I want to use, right? So it's totally up to you which flippers you want to use. So it would be 1/2. So let's say I chose the flippers 20 and 15. So if I chose those as my flippers, right? So now if I'm going to pick 20 and 15, then I've got to pick angle P, right? So that would be the sine of 29 degrees. So again, it's totally up to you which one you pick. And depending on round off error, right? If you pick different flippers, you might get a slightly different area. I got 72.72 square inches, but again, or centimeters. I think we're in centimeters, aren't we? Yep, centimeters. Right? Or actually, it looks like, looks like I've got a mixture of units up here, don't I? Whoops, that was a typo. All right, we'll go with inches then. All right, so we'll say inches squared. All right, so that is it. All right, good luck with that. Try some of those problems, and I will see you soon.